Okay, like I said, let me talk about some of the calculations that I've done, and then I'll answer your questions on the color generator spreadsheet if you're having any troubles with any of the steps, and then we'll talk about what to do when we want to model a big molecule and we don't have the time to get it done. Yeah. And then we'll look online for some candidate molecules, but again, it's some of them are just way too big to finish. Now, of course, you've got a whole week of Thanksgiving. Maybe you could finish one, but we could at least build the spreadsheet based upon a smaller molecule and generate the color of that. So let's look at some of these molecules that I've built. Let me start with again, if being an impatient person like I am, I just did azulene with a UFF. So universal force field, which is molecular mechanics, which takes just a few seconds to do. Okay, that's not right. I don't think this is AM1, it says. Oh, and I also played around with the asymmetry parameter. Yeah, so I cheated on this one. Okay, so I did point. So look at this. I was like, I know this molecule is blue, right? But if I do the parameters that I put in Blackboard, it's not blue, right? Yeah. Now, if your peak is in like if you have an experimental spectrum, and you have the Gaussian calculation, and it puts this peak right at 550 nanometers, and you look at the experimental spectrum and you see that it tails off to the 700s, like see this one does not tail very much to the long wavelength side. So my asymmetry parameter is going the wrong direction. If I were to tail that to the red side, so 1.5, see how that peak now tails to the long wavelength side? I guess for your perspective it goes the other way. And then I update the colors. You see now it's blue, because it's absorbing progressively more and more red. This region down here is is really affected by this asymmetry parameter, this 1.5. And so let me go back to 0.9. Okay, so I'm going to do undo. It's going to go back to 0.9. Oh, I guess it won't. Okay, 0.9. You see how that region has changed dramatically down here? It's no longer absorbing that red region. And if I update the colors, we see that it still lets a lot of the red through. And so in order to get a more accurate position for this peak, I went ahead and redid this calculation using, I did AM1, and then I did B3LYP. So here's the B3LYP spreadsheet. So this is azulene using a higher level of theory, and that peak has shifted now from just under 550 to now almost 575. Okay, well, it shows right up here, 569. Okay. There's a lot more peaks just because I just pasted all of them in here. And this one's coming in a really, really dark blue. I was playing around with the different concentrations too. So it's almost like a violet. We're still letting this red light through. Maybe my widths, if I wanted to play with those. Yeah, and so it's more like a grayscale as it absorbs both all of the green, a little bit of the red, and a little bit of the blue. If it's absorbing the red and the blue at the same time, then it almost looks like it turns gray. It's like a violet gray. Okay. Yeah, it's very interesting. Then I started playing around with other molecules. First of all, is everybody comfortable with the steps it takes to make a spreadsheet like this? Are you comfortable with the extraction of the ZINDO output? So here's what I've been doing. I finish a calculation, like let's see. Let's let's do this one. So I finish a calculation. Here's the log file. Okay, so this is the Gaussian output. And then I just start going down with the page down key. These are pretty short output files compared to the OptFreak, because this is not doing an iteration like an optimization. It's just a single energy calculation, calculating the excited states. So then I get down here and I start to see the transitions. So here we are, the excitation energies and oscillator strengths. So from this point down, I hold shift and start doing down, and it's selecting all of that text. So when I get to this point, I can hit Control C to copy, and then I go to my Gaussian spreadsheet, select all this stuff that I don't want, hit delete, and then I hit Control V and paste. Now it's all pasted in the first column, so I just leave it selected and come up here and sort Z to A, and I get all my excited states up here. So that's pretty fast. And then I grab these guys and go to the data ribbon, text to columns, and we do delimited, which means it's going to divide the columns based on a particular character. And so I hit space, and see now all the columns are divided wherever there's spaces. But I want this one here, F equals, okay? And so I want to get those oscillator strengths by themselves, and so I do other here, and I do an equal sign. And so then that allows me to split the F equals. Then I'm ready to go on. I could go in here and say don't import any of the other columns, or I could just hit finish. And then here's my wavelengths, and here's my intensities. I just grab both these columns, go to the home ribbon and delete them, and here now I have all of this. I can just grab this, copy it, go to my main page here, and paste it in. And so that's the spectrum. Now it doesn't update the colors. I can show you this macro for the colors, but I've got this nice button that will update the colors. And so this is a yellow compound that turns orange. And this is the triarylmethine. So let me open up that molecule. When I teach the forensic chemistry class, we talk about triarylmethynes, and let me just open Gauss view. That's one of the chromophores for pigments and dyes. These different extended ring systems all joined to carbon in the middle. It's a very stable cation. It could also be a free radical. See if I can drag and drop this. Probably not. Yeah, there it goes. Okay, and so then let's do this one up here. So this is the one I just did, I think. No, that was the amine. Okay. So I wanted to look at this molecule here, this triarylmethine. You see that's instead of a methane, it's a methine. We've lost a hydrogen. We've just got a single carbon in the middle, no hydrogen. And, you know, when we draw these molecules, we draw them flat because we don't show the hydrogens, but those hydrogens sterically bump into each other. And so these things are rotated a little bit. And that's what took this calculation so long to finish. It was quite annoying, as you might imagine. Right? Yeah. And so we can go to the, you know, any one of these. Let's see how long this one took. So control end and get us to the end. 19 hours. Yeah.
I'm already past that.
Yeah.
Child's play.
Child's play. While you wait, as we say. Yes. Yeah. So here's the, I mean, there's quite a few atoms. Coming up here. These are all the bond lengths and angles, as you might imagine. Does it say just straight up how many atoms there are? I don't have to count them all up.
It didn't know, so there's 40
Say again?
on the.
Here we go. 34, yeah. So the atom number is 34. So 34 atoms, and it took 19 hours. Yeah. So how many atoms does everybody's molecules have? What was yours? 88. 68. Okay, Rachel. 47. 82.
65.
65. 28.
If I drew it correctly.
I can't hear you. Are you looking? Yeah. Okay. Okay. 96. Okay. Yeah. Yeah. What was yours? 12. Yeah. She wins 12. Yeah. 24. Okay. Yeah. Are you counting them up? Yeah. $28. Okay, that's great. So, so how, like, if you wanted to panic, or not panic, if you wanted to, what do I want to say, bail on your molecule, you can do two things. You can go to a lower level of theory, like AM1. It's still going to be the same exercise, right? Or even UFF. I would go to UFF first so that you know you've got everything you need. So it's the same exercise from beginning to end. There's nothing wrong with that. It just will probably be less accurate in terms of the geometry, right? And the geometry will really make a big difference in the color. Okay. Then that's right. But you don't know how long it's going to last. You know, that's the thing. If you knew, then you could make a calculation. So this is part of the joy of Gaussian, okay, in quotes, is that you just don't know, you know. Yeah, so, yeah. So there's also ways you can restart calculations. That's in that the book that goes with this course, the Forsman and Frisch book. There's ways that you can resubmit a job with the checkpoint file, because all of that stuff, all the temporary stuff is saved in the checkpoint file. So if later on you don't want to throw away the 19 hours or whatever, or 28 hours that you have in the calculation, you can restart it. But, you know.
Does it pick up where it left off?
It's close. It picks up close to where it left off because it saves all of those wave functions in the checkpoint file. And so then it pulls up where it was before with all of the electron cloud and everything. And this is an electronic structure calculation. And so all of that scratch data is saved. Okay. So, yeah. Yes. So let's look for, or the other thing you could do is pick a different molecule. Okay. Yeah. There's the triaromethynes. There's also azo dyes. So if we type in azo dyes, you know, we can look at the different kinds to see. You know, this is a small one here. This is the Wikipedia page. Let's just go there and check out, see what they've got.
Is that going to use a charge molecule?
Excuse me?
Is that going to use a charge molecule?
Yeah, so you can, let me show you that. So if I have a charged molecule, like in this one, I went ahead and thought, you know, instead of doing the free radical, because it's to be an odd number of electrons, right? A lot of these are cations. And so they'll have a counterion, like a chloride counterion. We don't have to do the chloride counterion. In fact, don't, because it will try to find the position of that chloride. And that chloride will walk around the molecule trying to find its happy place. And it's going to take forever, you know. And the molecule's fine, but the chloride's moving along. And, yeah. In fact, that was really cool one time. I had a copper. I was doing copper and water. So I had copper and 6 waters around it. And we know that cations, especially 2 and 3 charged, cations like copper 2 plus and aluminum 3 plus are acidic, right? Why are they acidic? Well, they pull that water so close that it exposes the proton, and the proton can come off very easily. It makes a very acidic proton. Well, this optimization of the water positions was taking so long because one of the waters got pulled in and the hydrogen popped off and was like moving around the complex. It was totally a movie of the acid-base reaction, the autoionization reaction. I made a copper 2 single hydroxide species with the proton moving around the electron cloud. It was so cool. And so in Gaussian, if you do an optimization, you can watch what's happening with each of the steps. So what I was going to show you is how to do a cation. Okay, so here on the Gaussian, when we set up the calculation, then under optimization, or any of those, actually, no, that's fine, energy is fine. It's this method tab. Here's the charge and multiplicity. So you could make it, 2 plus, 3 plus, we could go down to -1, -2, and so on. So we could do the anions as well. So I could see, maybe I could see what the anion of this is, and it's also a singlet, So we could do the charge species that way. Okay. Let me show you. Yeah, I'll just go ahead and bring this. Let me close these out, and I'll bring in one optimization and show you how to show the intermediate steps. And so if I pull up, yeah, let's do this one. Oh, I have to actually open it with this. So when you to do this, you need to use the file open. So file open, and you get this dialog box. And down here at the bottom, it says read intermediate geometries. So that's a neat little checkbox. And so if we pull up, I want a more floppy molecule because it'll be interesting. Yeah, let's do this. Let's do this one. Okay. So this is my, I brought in that initial guess, and under optimizations. Oh, I may not have. Yeah, because I didn't get the option. Okay. Let me try it again. So you do file, open, check the read intermediate geometries. And I'm going to pick this triaromethine B3LYP optimization. And I think that's it. You just click that read intermediate geometries and hit open. Yes, so now you have this little play button up here. Yeah, it was a little fast, yeah. You can show this view. Let's see, where is it? Tools, results. Optimization, it's under results. Okay, so this is cool too because it's showing us we're at the end here, but let's go to the beginning. Let's see, we can click it. So that was my initial guess. So my angles, my dihedral angles were like 60 degrees here. And that was obviously a high energy. And so then we go to optimization 2, see how those dihedral angles change. So this was the first step, then the second step, then the third step, and the fourth. It changed the axes, and when it changes the axes, the whole molecule like dramatically jumps. And so it's oscillating back and forth, and then it found the minimum. So this one took, let's see, how long did this take? Summary. So on the results page, there's a summary, and it says 1 day, 3 hours, 12 minutes.
How many hours?
27.
27 hours. And this is a small molecule. But it was all those dihedrals and calculating. And you have 96, was it? Yeah. Yeah, so Don't know how that's going to go for you.
I don't think yours has a ton of dihedral angles in it, though.
It's the dihedral angles that really take a long time. You see, that was really the only thing that we could tell was changing in this molecule. Yeah.
There was something that said dummies. What does that mean?
Yeah, dummies. There's an option in some of the molecules for you can use dummy atoms that are they're useful for defining the geometry, and so they don't have they're really not part of the calculation, but they might be part of the structure. That's helpful if you have a complicated reaction. You're trying to say do a reaction mechanism, and you want, say, the center of both of those molecules to be controlled, and the angles and everything that as they approach. You can set up some dummy atoms and then define all of the molecules relative to that spot in space. So you can draw them together, right, and then maybe have them twist or something like that. But anyway, that's what a dummy atom is. And I'm showing, it says it's clicked, so I'm showing the dummy atoms, but we don't have any. Yeah. No, that's a great question. Yeah. Now, this is interesting. Under results, they've added UV-Vis here. Now, it's grayed out because we don't have that information in this file. But if we open up the .z version, I go ahead and add in I put a Z on there when I do the subsequent ZINDO. So this is the triaromethine Z here. So OZ log. So if we bring that one up, so here's the ZINDO of that same structure, and now under results we see UV-Vis. And so it does the convolution for you, and you see all the oscillator strengths and everything, but you don't really have any control over all of the widths and heights. It's I don't even know what line shape they're using. It does this ECD, electronic circular dichroism spectrum. You'd have to read up on that. Yeah. So there's it's funny. One time I was in a seminar in grad school, and this fellow's giving his talk, and it's a great talk. I don't even really remember the topic, but one of the professors asked, is this similar to so-and-so's equations, right? And the guy said, yeah, that's exactly right. And you do this and this and this, and this is how you model it, and so on. And after the seminar, I told the guy that asked the question, he was my Cation professor, my thermodynamics professor, and I said, you mentioned these equations or whatever. I've never heard of them. Never once. Not even, it's totally foreign to me. And he looked at me, and I said, but I'm almost done. And he just laughed. He said, you think we tell you everything? He said, we can't possibly teach you everything, And so what is electronic circular dichroism? I don't know. No one taught me. Yeah. Right? And I'm not teaching you. So I can't teach you what I don't know, But I'm hopefully teaching you how to learn, right? If you learn how to learn, you learned enough. And so then that's a famous quote, but I forget who wrote it. It was on a building outside at Oregon State. He who's learned how to learn has learned enough. And I was like, good, I'm done. Give me my PhD. So I had to do a few more things. But anyway, it was a great quote. I was like, I'm going to try to use this on my advisor. Yeah. So yeah, you can go online and find colored molecules and hopefully get like an idea of what their color would be. There's all kinds, but like this one, trypan blue, probably not a good one to choose, right? Yeah, that's a lot. That's too many atoms. Okay.
It's pretty symmetric though.
It is. That's right. But you got all these dihedrals and these SO3 groups. Those are really. This is a food. I think this is probably one of the food colorings, because these SO3 groups are what make it soluble in water. Okay, so they really don't contribute to the color. Now, how do I know that? I can't be confident, right? And that's the exact purpose of this kind of exercise. So just take maybe this phenyl ring here, throw that methyl away, just put a hydrogen there, and model half of a molecule like this with the sulfonate groups, get the color, and then take those things off. See, that's how you would tell, are these sulfonate groups changing the color, or are they just there for solubility? And that's a perfect example of the use of this kind of modeling. It's like you could see if those acid groups are contributing to the color or not. Are they essential? Would it matter if I used a carboxylic acid group or a sulfate? You know, and you could swap those out and see if it changes the color. So that's a perfect example of the usefulness of this color modeling. Okay, so you could go back to this original azo up here, you know, and instead of the OH, you know, you do the OH, you do the sulfonate, you do the carboxylic acid, you know, you do a nitro group, you know, carbonyl. So you could take these parent molecules and then you can change the different features, and then y'all can compare your results to each other and say, look, when he had a nitro group, it was green. When I added a nitroso, it shifted over and it was orange or something like that. Just a small change of one atom, boom, you got a huge color change. Sometimes, if it's those N to pi stars coming off the nitro group and going onto the ring, then you may have a huge change in color. So, it's up to you. How did yours turn out? Did you finish your molecule? Not yet? Okay. So talk to me about your progress on making this kind of spreadsheet, though. I know everybody's working on the Gaussian, but...
That specific page,
the main page?
That part right there, did you make that?
Yeah, so I built these other sheets, okay? And so then I like grabbed this plot. I think you can just paste it onto the front page. Let's see. Yeah, so it still refers back to that data. So it's referring to the convolution page. Now, how do I get this beautiful rainbow? So right click on the back, or just double click on the back of that plot, and you get the format plot area. And then you can do fill, and you can do a gradient fill, I believe. Okay. And we want a linear gradient, yes. Direction, we want it to go left to right. I thought there was a pattern, pre-filled one, pattern fill. Picture, texture. No. I thought it was a preset. It used to be. Oh yeah. Where's the color?
Down.
This guy. Yeah, but this is like a solid color for this particular gradient. Like you can come over here and you could do blue on that far side, and then you could do, you know, around here you could do green. You could make it yourself, but this rainbow thing, maybe I put it in as a picture. No, I built it. Yeah, so that's ridiculously tedious. I'll send y'all this file here. I've been in contact with a fellow in Costa Rica who likes this RGB lab and this color predictor, and he sent me a background image that is accurate, the rainbow, you know, with the wavelengths. And I'll have to write myself a note because it's buried deep in my research folder.
I'm disseminating.
Yeah, please do, so that'll remind me. But then you can, what you can do is you can use this picture, and you can put a picture in the back, like this picture source, insert, you know, you could probably find one online. Right here. Yeah. I mean, let's do this one here. Insert. But you might like save that picture, go find that picture and crop it. But you can insert a picture like that. And so that's how I did. Now this is backwards, right? So the red is on the wrong side, but yeah. So that's how I did that, was I put that in the background. Now actually it looks like I built the gradient myself down here, but you can go in and get a picture and put it back there that has those colors so that you can kind of see this is absorbing the blue, therefore it's giving us a yellow color. So that's why I think it's nice to have this, but this, you know, sort of rainbow image in the background. Yeah.
Does it go back to purple in this way?
Over here,
Yeah.
if that's the only light coming through, let's see, let's make it happen. What do you say? Okay. It looks like this last one looks black almost. We're not quite getting that color. You know what I'm saying?
Yeah.
Let's undo that. And let's just march this peak width over 60, 100, 0.9. I want it to be sharper. Okay. Okay. Let's move it over to 500. Still turning black. But these are the kinds of questions you could ask. Like say, what happens when I only get like 680 to 700?
Right.
You know, what that pinkish purple color really only comes when you have a little bit of blue with a little bit of red. Yeah. Now it's nice when your dye, like the azulene, we know it's blue, and so you know kind of what your target is in terms of the color. But like if this one, if I'm changing this to a nitro group or something, you really don't have an absolute reference for the color. And so what you're going to have to do is probably do two of those molecules. Like here's this says it's an orange colored azo dye. So you know this one is orange colored. So if you put a nitro there, then maybe you can model this one and you've got it orange, which will tell you kind of if you have the peak width right and the peak asymmetry correct and it's giving you orange. Then the only thing you change then is change it to a carbonyl or something like that, or deprotonate it, make it an anion, or make it a, you know, something like that. And then you can look at that compound and see if the color changes. So you're really just sort of looking at, okay, if I do this functionally, the color changed a certain way. And that would be an interesting, you know, way to determine, okay, if you really want a new dye that's not orange but has a slightly different color, maybe a more orange red or maybe yellow orange or maybe a blue or green, you just change these functional groups. And you know, if you were to do this like they did with the azulene, they put aldehydes on there, they could use the electron withdrawing or electron pushing character of the substituents and determine which way the wavelength was going to shift. And so they put the aldehydes on there, and that extended the box. It was withdrawing, I believe. I'm not an organic chemist. And essentially the way I think of it is it extended the electron box and caused it to redshift. And so we started to see it become kind of purple colored because it started letting blue through. They put fluorines on there and it pushed the electrons back onto the ring, and that caused a blue shift. And so then that molecule became a different color. So it's kind of an interesting thing. So you could do that with different functional groups if you wanted. Once again, once you build this spreadsheet, it's super easy to do another molecule. You just do another Gaussian calculation. If it's small, it'll finish in a reasonable amount of time. You do the ZINDO, and then you just come over to your file manager and you copy that spreadsheet and give it a new name and put the new molecule's peaks in there, and you've got a new color for the new molecule. So you don't ever have to rebuild this spreadsheet once you built it once. You just copy it, change the name, paste in new peaks. So it's super easy. Once you build this tool, then you just use the tool for the different molecules. And then I would love to see that. So I'll give you some guidance on what I mean by student presentations. I'll send it out on Blackboard. But what I'm thinking is I'll give you sort of a sample template to use in PowerPoint that'll say, here's a page that you need to put a structure of your molecule. Just paste it in from Gaussian, okay? This is the molecule I did. These are the features I was looking at, sort of like here's the molecule I was interested in, here's what I did. And then a page that says computational commentary, did it finish, how long did it take, and how many atoms, and that kind of thing. Any errors, any kind of unique things you had to do to finish this calculation. And then show something like this. Yours doesn't have to look just like mine, but something like this where you see the absorption spectrum, the transmittance spectrum, the chromaticity diagram, and some idea of the colors that you get out of this molecule with concentration. Okay. So that's what I'm looking for. And so it'll be like a 4 or 5 slide thing. And so then we'll just go up each student after another to show the different colored molecules that we have. I think it'll be an interesting way to finish up. Okay. All right. So everything, I need to hear your questions. I don't want to leave and then you say, I have a question. Okay. This is the time for questions. Yes. It wouldn't run on Gaussian, the ZINDO? Okay. What does it say at the end of the output file? Singlet states only. Okay. So it says link died.
We changed the energy to this one. Job type, yeah. So the job type should be energy, not
Yes, job type. Yeah. Okay, so you do the optimization first, and that should be with B3LYP 6-31G with the D in parentheses. And then when that is finished, you have to open that log file. So you have the optimized geometry, and then you resubmit a new job with, and I always just put a Z on the end of the file name to tell me that's the ZINDO job. So it's energy on that job type tab. I'll just show again for everybody. Okay, so it would be here. So I would change this job type to energy. Method would be then, instead of ground state, we're doing ZINDO. So we're calculating excited states. Again, this is an odd electron species. I looked it up online and I found this molecule, and it was a similar molecule, but it had some nitro groups on the ends. It was called ethyl violet, and it was a cation. And so I thought, oh, well, then that makes sense. Maybe this should be a cation. And so I simulated the cation. So then that makes it a singlet, and then the states, I calculated singlets only, and then here I put 20 for 20 to solve for 20 states. Yes?
Calculate ZINDO after it already ran, right?
Yes.
Do
Okay.
the optimization, then do the frequency.
Yeah.
And don't do
In fact, you can skip the frequency. That'll save you a little time too. Because, I mean, it'd be nice to like look at it to see if you're at a global minimum, okay? So that would be the usefulness of the frequency calculation. And with a ton of dihedrals, you may want to do that. But again, we're just really focusing on trying to, I'm just trying to teach you the path of this calculation. Since we're not publishing any one of these molecules, or, it's not essential to anything, whether you got the right color or not. I'm flexible on that. If you don't do a frequency calculation, I didn't do a frequency calculation on these. I just wanted to show you the path to take to model color. Does this make sense?
The molecule is not charged. I mean, the charge is 0. Do we need to select the doublets only under the string?
Yeah, so this is the thing. When it's a doublet, then there's no way to, so I can't click anything. Yeah. So I ran into that too when I did the doublet. So the only thing I could do was just solve for more states, and I didn't have an option for picking this here. Yeah. So I just calculated this way. Yeah. Next question.
That's the deal drawing the molecules. If I have conjugated double bonds throughout like my entire molecule.
Mhm.
Would it be better to do the like the line and dash for everything, or put double bonds in one, double bonds in one, or whatever?
Let me show you what I got for this, the nitro, the amine one. So on this one here, the triarylmethine with nitrogens on the end. Look at all those delocalized electrons.
Yeah.
Like and I'm okay with that. That doesn't bother me at all. Okay, because I know what Gaussian's doing. It's saying those are all pretty short bonds. Okay, but look at that. I mean, even though they're twisted, it's showing that there's some delocalization of the electrons into that unused p orbital. Yeah.
But would it? Let's say if I did it all, I did it. Would it? I know an OChem affects the geometry. When it optimizes it, it's going to ignore whether I say it's double bond or that. It's going to.
Yeah, it has no. Yeah, there's nothing that you're giving it that tells it what kind of bond it is, because it's just taking the nuclear coordinates. Does everybody get that? So when on the input file, it does not look at what those double bonds or single bonds, that's irrelevant to Gaussian. It's just taking your nuclear coordinates and it's calculating the electron cloud. So even though this displays all of these, like double bond or 1.5 bond orders and so on, that's really irrelevant to Gaussian. Gaussian is calculating the electron cloud. These sticks are just a lookup to say this is trying to communicate to you that's shorter than a single bond. That's all it's doing. Okay. And you can come and change the view to under display format, under molecule, and this is ball and bond type, but you could just do ball and stick where it's just sticks. It's just not as satisfying to me. I like to see double bonds and those other kinds of things, but this is a more neutral way to display the molecule. If you're giving a presentation and you don't want to get sidetracked on it saying, that says that's a 1.5 bond order on this particular molecule, when bond order is irrelevant to molecular orbital theory. It's a fiction, okay? So you don't want to get sidetracked on that. Then you can display your molecule like this and no one's going to ask the question because they don't see these confusing ball and bond type, pictures, right? So you have total freedom of how you display your molecules. If you have a huge molecule, if you're a biochemist, then you probably want to do something like wireframe. Okay. Now it is hard to see. So what you can do then is you can pick particular layers. See, so if I designate in my molecule one of these, like say an R group that's important in an enzyme, and I can set that at the high layer, and then I can have the medium and low layers be wireframe, but the high layer can be ball and stick, so that R group by itself will be the one shown as ball and stick, and the rest of the enzyme, the backbone and everything else will be wireframe. It'd be great. And then you can rotate the whole thing around and you can see that, let's say you have all of the R groups on a pocket displayed with high level or high layer, then they will display with ball and bond type or ball and stick, but everything else will be wireframe and you can see through it. So it's a really great tool. And you'll have to go on to Gaussian help to learn how to tell Gaussian which is in the high layer, which is in the medium layer, which is in the low layer. Now, they won a Nobel Prize for programming Gaussian and other software packages to do different levels of theory based on these layers. It's called ONIOM is the thing. I can't remember what the acronym stands for. It's shame on me. But it's they can do ab initio on the high layer and molecular mechanics on the rest of the protein. Yeah, and so that's fantastic. So like if you want to do, or DFT, if you want to do a density functional calculation of the lock and key mechanism for an enzyme, that's too big because the enzyme, there's no way you're going to do B3OYP on an enzyme. Forget it. But you could do B3OYP on the high layer with like 200 atoms, it'll take a while, okay? But then going to the medium and the low layer, medium may be AM1, and then the low layer, molecular mechanics. And you can put 3,000 or 4,000 atoms in here and do B3OP on the pocket. And that way you know that this side of the pocket and that side of the pocket are connected through this alpha helix and all this other stuff. So they're accurate. If you cut all that stuff off, they may not be accurate. And so then your binding energy wouldn't be calculated correctly and so on. So that's the way that you can do this, and that's what this high layer, medium layer, and low layer are. If you have that defined in your molecule, then you can come here under display format, and you can pick the different types of displays.
So this is a general question. When I was building my molecule, I'm using red, Congo red.
Yes.
This is molecule.
Yes.
So I noticed the connection between each atom as I was building it changes, like the bonds between this nitro group and this carbon. So the bond was increasing gradually. So I don't know the cause of that.
Oh yeah, I don't know either. Yeah. So as you as it's optimizing, you can see it increasing.
Yeah.
Yeah. Sometimes, I mean, in the past, sometimes I've made mistakes, like on the charge or something, and then a group will come off, like kind of like that copper water complex, yeah. But that's a huge molecule, so you may want to just see what one part of it would be. Like, is one part of it enough to give you a color? Yeah. If you can break it into a smaller piece, or take one of these smaller analogs online and try to model them. The smaller the better, just so that you can finish. Yeah. I should have really emphasized that earlier. I'm sorry. Yeah.
I don't think I knew what small meant Gaussian.
Yeah. Okay. So it's definitely. I mean, to me, that's a learning thing too. I don't ever like it when people say, well, you bump your head and you're like, well, you learned a lesson, but it is a lesson, you're like, yeah, if you're trying to do B3OIP, you're not going to get around, it's not going to be done in a day if it's 100 atoms, Or mine took a day and 3 hours and it was only 34 atoms or something.
Yeah, that's
like
what
that.
made me nervous.
Yeah, exactly. All right.